Hi, this is Professor Fernandez. In this video, we're going to work out an example of geometric series convergence or divergence and how to find their sum if they converge. So the example we're working out comes from lesson 6 in this Calculus 2 course. If you'd like to download the lesson or take a look at some of the other resources, head over to that site. So let's take a look at the example. I'm going to zoom in here, determine which of the geometric series below converge and find their sum. So remember, as a quick review, a geometric series looks like AR to the n. We often start at n equals 0, not at n equals 1, but that's not absolutely necessary. And what do the terms actually look like? Well, if n equals 1, a times r to the 0, that's just a. If n equals 0. If n equals 1, a times r to the first, that's ar. And then ar squared, and so on and so forth. So you can see that we get each term by multiplying the previous term by r, right? So multiply that by r, you get that term. So that makes it a geometric series. So it also makes it possible, for example, to write geometric series in sigma notation. So here is, let's see, here is a geometric series. I'm just making it up on the fly here. This is a 3. So if I wanted to write this in sigma notation, first of all, I have to determine it's a geometric series. I could do that by just running it through this test. If this is A and this is AR, well, then what is the number that I had to multiply 3/2 by to get this one? There's a 2 squared down here, so that's 1/2. So 3/2 times 1/2 gives me 3 over 2 squared. So A is 3/2 and R is 1/2 based on these two terms. And then does this work to reproduce the third term? The answer is yes, because if I start here and I multiply it by 1/2, I get 3 over 2 cubed. So then I can say, oh, A is 3/2, R is 1/2, so I can write this series in sigma notation as sum from n equals 0 to infinity of A 3/2, that's a 3, times R 1/2 to the n. Okay. So again, this is a really quick review, sort of summary overview of what a geometric series is, how you spot it, how you kind of determine A and R, and then how you write it in sigma notation. Okay, so now to the example itself. How do we determine convergence or divergence for a geometric series? I'm going to zoom in here to this theorem down here. This is the theorem in lesson 6 of the lesson notes. So what does it say? It says the geometric series, there it is, converges to, wow, we even know what it converges to, right? A over 1 minus r, provided the absolute value of r is less than 1. Okay, so a couple of things there. First of all, this is a theorem for a geometric series, okay? Second of all, the convergence depends on r. So it really does pay to be able to identify r, which is one of the reasons I just reviewed it a minute ago. And if r is between -1 and 1, then the series converges, and it converges to A over 1 minus r. You know its sum, so that's really nice. There aren't a lot of infinite series that we know the sum formulas for, but geometric series is one of those really nice ones where it is in that category. And then the series diverges if absolute value of r is greater than or equal to 1. So two things, right? Greater than 1, right? So an absolute value. So either r is like 2, 3, 4, 7, in other words, bigger than 1, or less than -1, like -2, -10. So greater than 1 in absolute value, or equal to 1, right? R equals 1, the infinite series, the geometric series is going to diverge. Why? Because if r equals 1, this isn't here, this isn't here, this isn't here. We're just adding A to itself, you know, forever, right? And that that series diverges. Okay, so takeaways. Number 1, if you know it's an infinite series, we talked about how to spot them earlier in the video, then all you have to do is compare the r value to this range. If r is between -1 and 1, it converges, and it converges to A over 1 minus r. Otherwise, diverges. Awesome. So going back to the examples up here, is this an infinite series? You know, if you know, I'm telling you they are, but again, in the interest of helping you develop that skill of spotting infinite geometric series, is this a geometric series? Yes. How do I put it in that form? Well, I can write this as 5 times 1/4 to the n. So this is the A, this is the r. And again, it's useful to be able to do that, right, as a skill, because we need to identify R for convergence purposes. So in this case, R is 1/4. So that tells me that 1/4 is definitely between 1 and -1. So implication is that series converges, and the sum is A over 1 minus R. Right? So what was that? In this case, A was 5 and R was 1/4. We could leave it that way, right? That is the answer, not simplified, but I'll do a little simplification. So 5 over 3/4, that's 4/3 times 5. That's 20 over 3. Okay, so we have found not only that the geometric series, the earlier one, right, 5 over 4 to the n, converges. We know what its sum is, so that's pretty cool. Okay, let's keep going here. What about B? So part B, this is a different series, right? You can see that it's very similar to the one, and this is why I wrote it this way, that we just did, except we've kind of changed things in a very subtle way. So this is now the R value. R is 5/4, right? And the A value, what is the A value? Well, it's kind of hidden. There's a 1 there. So A is 1, R is 5/4. Question, is 5/4 between -1 and 1? The answer is no, right? 5/4 is 1 1/4, which is 1.25, so that's bigger than 1. So this series diverges. Okay? This other one converged, and it converged to 20 over 3. Okay, so moving on to part C, right? This one is an interesting one. And, you know, one of the reasons why it's interesting is because we don't see a number here, any numbers, right, for the a sub n term. We see a variable. Nevertheless, right, here's how we can treat this series. We can say let x be a fixed number. In other words, let's consider the series, for example, I don't know, 2 to the n, and then analyze that as a geometric series. And then go back and consider, I don't know, 1/2 to the n, analyze that. So in other words, even though there's an x here, x is a number, right, that is fixed for the purposes of analyzing this geometric series, as if it was 2, or as if it were, 1/2. So we're going to proceed then to do the same thing we have just been doing, except rather than using an R value that is a number, we're going to realize that in this case R is x, a variable. But again, we're thinking of it as a fixed number that we have yet to pin down, a parameter. And then the a value once more is hidden, so a equals 1 here. Okay, so what does the geometric series theorem tell us? Okay, scrolling back down here to remind you. The geometric series converges to blah if blah. Okay, so I'm just going to write this over for this particular series, and then I'll talk about how it is implied in a way in the theorem. I'll just say in English, converges to a, which is 1, over 1 minus r, which is x, if absolute value of r, which is x, is less than 1. And diverges if absolute value of r, which is x, is bigger than or equal to 1. Okay, this is literally, I just wrote out the geometric series theorem for this particular series, and this is what it turns into, right? So another way to say this is that the sum from 0 to infinity of x to the n equals 1 over 1 minus x if absolute value of x is less than 1. And now this is where I'm going to do what I said I was going to do earlier. If you look at the geometric series theorem, right, it's a small infinity sign. If you look at the geometric series theorem, it's AR to the n, and it converges to a over 1 minus r if absolute value of r is less than 1. Compare these two statements. They look pretty much exactly the same. The only thing that is different is, first of all, the a value is 1, so I'm going to remove that. There we go. And then second of all, I just literally changed the letter, right? This is r, this is x. This is r, this is x. This is r, this is x. But things are radically different now. And the reason they're radically different, and the reason, therefore, why I put this example here to illustrate this point, is that in the first two examples that we just worked on, these were geometric series, what I would call honest to goodness geometric series, in the sense that they had a bunch of numbers in them. These are things that you study first in calculus too, and then you move on to things like part C. But we analyzed them using the theorem, and we got a sum that was a number. Here, in this case, it diverged. There was no sum. Here we are seemingly analyzing something totally different, right? There's a variable, there are no numbers, and we're thinking of S as fixed to try to make it a number. But at the end of the day, like, the conclusion is just effectively a restatement of the geometric series theorem itself, where you replace R by X. Okay, but the big reveal then is that we're going to come back to this results on and on in the course, because this is, on the left-hand side, an infinite series involving a variable. So we're going to have to make sense of this in some way. And on the right-hand side, this is a function, 1 over 1 minus x. We can graph this function. And what this equation is telling us is that these two radically different objects, an infinite series and a function, are equal, provided absolute value of x is less than 1. So I'm trying really hard to imbue this result with a lot of mystery and awe, so that we can later on try to unpack it and figure out what really happened. At the same time, I do want you to also take away that, if this is the result, then I can just go in here and, like we did, effectively change the letter, right? But know that it really isn't that, the story doesn't stop there. If you change a letter, letters have meaning in math. So R, in the context of this theorem, we were thinking of as a number, right? And that's how we used it in parts A and B here. Whereas in part C, R has now become a variable. And again, a variable gets pinned down to a number if you choose x equals 7 or something. So, there's a way to connect these things, and I've been doing that throughout this discussion. But long story short, this is an important result, right? This geometric series on the left-hand side, its sum is 1 over 1 minus x. It converges to this quantity, provided absolute value of x is less than 1. If absolute value of x is bigger than or equal to 1, it diverges. To finish up, some special cases, right? What if x is 1/2? Okay, well, absolute value of x is less than 1, converges. And converges to 1 over 1 minus 1/2. Great. Another special case, what if x is 17? Right, this one diverges because absolute value of x is bigger than or equal to 1, right? X in this case is 17. So you can see that from this one result, I know it's getting cluttered, sorry. From this one result, we can just pop out a whole bunch of different series of numbers, infinite series containing numbers, and get all sorts of convergence or divergence results. So that's another way in which this, overly crowded rectangle containing a really important result, right, is indeed very interesting. Okay, so that's it for now. Thanks for watching.